Ever thought about how earthquakes subtly shift the Earth's gravity? It's not just about the shaking, it's about the Earth's mass moving around.
Exactly. It's a fascinating interplay of physics and geology. We can actually measure these tiny shifts in gravity.
Tiny shifts. How tiny are we talking?
We're talking microgauss, sometimes even sub-microgauss. You need incredibly sensitive instruments.
Wow, that's mind-blowing. So what kind of technology are we using to detect these changes? So traditional gravimeters have been around for a while, right? But what's the state of the art now?
Absolutely. Traditional gravimeters were crucial in early studies, but now we have superconducting gravities, incredibly precise instruments that can detect changes at the sub-microgal level.
Right. And then there's space-based technology, right? Like GRACE?
GRACE was revolutionary. Twin satellites measuring the distance between them, giving us global gravity data. It filled in the gaps over oceans where ground-based measurements are difficult.
I see. So GRACE gave us a global view, but what about finer details?
That's where GOES comes in. It measured gravity gradients, giving us much higher resolution data, especially useful for near-field studies.
Okay, so we've got the measurements, but how do we interpret them? What's the theory behind it all?
That's where seismic dislocation theory comes in. It's the mathematical framework that links fault movement to the resulting changes in the gravity field.
And it's not just a simple equation, is it?
No, it's evolved over time. Early models used a semi-infinite medium, but more recent models use a spherical Earth, which is much more realistic. They even account for the Earth's layered structure and viscoelastic properties.
Viscoelastic, what does that mean?
It means the Earth isn't perfectly elastic. It deforms and recovers over time. This is crucial for understanding post-seismic effects.
So what can we actually do with this theory and these measurements?
A lot. We can invert the gravity data to estimate fault slip distributions, seismic moments, and even regional viscosity structures.
Viscosity? Like how gooey the Earth is?
Exactly. Understanding viscosity helps us model post-seismic deformation.
And what about earthquake prediction? Can we use gravity to predict earthquakes?
That's the holy grail, but it's still a long way off. There's evidence of pre-seismic gravity anomalies, but separating them from other signals is a huge challenge.
I've heard about pre-P gravity signals. What are those?
These are incredibly fast signals that arrive at seismic stations before the P waves. They're caused by the initial density changes from the earthquake rupture.
So they could be used for earthquake early warning?
Potentially, but they're extremely weak, and separating them from noise is a major hurdle. Artificial intelligence is showing promise here.
What about the gravity changes between earthquakes? The interseismic period?
That's a relatively new area of research. There's evidence that interseismic gravity changes might reflect slow strain accumulation, potentially providing clues about future earthquakes.
So it's like a slow buildup of pressure, detectable through gravity?
Exactly. It's a subtle signal, but potentially very important.
Does this gravity stuff apply to volcanoes too?
Absolutely. Volcanic eruptions involve mass movement, causing detectable gravity changes. It's a valuable tool for volcano monitoring.
So it's not just earthquakes, but a broader range of geophysical phenomena?
Precisely. It's a powerful tool for understanding the Earth's dynamic processes.
So what are the biggest challenges facing this field?
Separating earthquake-induced gravity signals from other sources of gravity variation is a major one. Hydrological effects, for example, can be significant.
Right. And what about the technology?
We need more sensitive instruments, better spatial and temporal resolution, and more sophisticated data processing techniques. Quantum gravities hold great promise.
And the theory?
We need to improve our models to account for three-dimensional Earth structure, topography, and the effects of fluids in the Earth.
So, to summarize, measuring earthquake-induced gravity variations is a powerful tool for understanding earthquakes and other geophysical processes.
It's a field with huge potential, but also significant challenges. The combination of advanced instrumentation, sophisticated theory, and clever data analysis will unlock many more secrets of our planet.
It's amazing how much we can learn from these tiny shifts in gravity. It's fascinating how this research connects so many different aspects of geophysics, from the fundamental physics of gravity to the complex processes of earthquakes and volcanoes.
It truly is interdisciplinary. The more we learn, the more we realize how interconnected everything is.
And the potential for earthquake early warning is particularly exciting. This discussion has been really eye-opening. Thanks for sharing your expertise.
My pleasure.
It's incredible to think about the level of precision involved in detecting these minute changes in gravity. That was a great discussion.